Everyone. So today we are going to finish the linear algebra portion of the course, and then hopefully we're going to start the mechanics part, and we're going to talk about, hopefully by the end we're going to talk about the stress matrix. So the first part that we're going to talk about today is symmetric matrices. And as we said, symmetric matrices are very important because most of the matrices that we deal with in solid mechanics are symmetric matrices. The stress matrix is a symmetric matrix, the strain is a symmetric matrix, and even when you do a finite element analysis, the stiffness matrix is a symmetric matrix. So it makes sense that instead of studying all these matrices by themselves, we can just study what the properties of a symmetric matrix is and then apply it to all these other matrices. So the definition of a symmetric matrix is that S is equal to its transpose. Or in other words, Sij is equal to Sji. Or for any two vectors in Rn, u dot Sv is equal to Su dot V. So let's look at what a symmetric matrix does first before we continue with the abstract proofs. So we have agreed that I have the graph here already. Agreed that any symmetric matrix or any matrix takes a circle of vectors and gives me an ellipse of some sort. Now, if S is symmetric, then the following is guaranteed. There has to be one vector that will get longer or shorter and stays in the same direction. And the vector that's perpendicular to it will also be an eigenvector of S. So basically, when S is symmetric, you're guaranteed the picture that you see this in 2D or in 3D or in any dimension. Now this is not guaranteed for any matrix. I'll give you an example. So, the above picture is guaranteed for any symmetric matrix in any dimension. Now, this is not always guaranteed. Let's, for example, consider Q, which is equal to cosine 30, negative sine 30, sine 30, cosine 30. What will Q do if this is a circle of vectors? This vector A will be rotated by 30 degrees. So all the vectors here will be rotated by 30 degrees. So QA, QB. Which means you don't have any vector that has the same direction. No vector keeps its direction. So this matrix, under the effect of Q, under Q, no vector keeps its direction. But under the effect of S, if S is symmetric, I'm guaranteed two directions that are perpendicular to each other to keep their direction after the effect of S.
So would it mean that there will be no eigenvectors for the rotation function?
Yes. No real.
No real.
You'll find some eigen, because this complex, yes. No real eigen values for this cube. Okay. So for a symmetric matrix, this argument is very important. The matrix is symmetric is equivalent to saying the following. It possesses three real eigenvalues, and it is possible to choose three corresponding orthonormal eigenvectors. The eigenvectors associated with those eigenvalues are perpendicular to each other. Now this applies also to higher dimensions. And the proof of this argument relies on a little bit of complex analysis, but let's say simple proof. Simple proof for S belongs to m power 2. For S belongs to, if S is a 2 by 2 matrix, to find the eigenvalues, you need to find the determinant of the matrix that looks like S11 minus lambda, S22 minus lambda, S12, and it's symmetric, so this will stay S12. This will be S11 minus lambda, multiplied by S22 minus lambda, minus S12 squared. If you equate this to 0, you'll find lambda is always real. Now, of course, if you want to do this for higher dimensions, the equations are going to get a little bit complicated. And so we're going to use a different proof to show that this is true for any dimension. And to show that it's true, we need to say the following. Should I lower the light, or you guys dim it? Dim it? going to assume that lambda is a complex eigenvalue for S. So we'll just argue by contradiction. Okay, what will happen if lambda is a complex eigenvalue of S? Then X is a complex eigenvector. And you have Sx equal to lambda x. Now if lambda is an eigenvector, an eigenvalue, then lambda bar is also an eigenvalue, where lambda bar is the conjugate if lambda equal a plus bi, where a and b are real numbers, and I is equal to square root of -1, the conjugate is equal to a minus bi, is also an eigenvalue. Which means that I can say Sx is equal to lambda x. So I have Sx equal lambda x, and Sx bar is equal to lambda bar x bar. I'm going to take the dot product with x here, and take the dot product with x bar here, and then utilize the symmetry of S. The symmetry of S tells me that these two are the same. Which means that lambda x bar dot x minus lambda x dot x bar is equal to 0, which tells me that the conjugate of lambda minus lambda multiplied by x bar dot x is equal to 0. Now, do you guys remember what will happen if I multiply a plus bi multiplied by a minus bi? I will always get a number that's greater than 0. Which means this has to be greater than 0. Which tells me that lambda has to be equal to lambda bar. If a complex number is equal to its conjugate, that means if a plus bi is equal to a minus bi, that tells me that b is 0. So, indeed, it possesses 3 real eigenvalues. All the eigenvalues are real. And it is possible to choose 3 corresponding orthogonal or orthonormal eigenvectors. So let's see what this means. We're going to choose, or we're going to pick lambda 1 and lambda 2 being 2 eigenvalues for S. Corresponding to 2 eigenvectors. x1 and x2. What I want to prove is that vector x1 and vector x2 are perpendicular to each other. Again, I'm going to do exactly what I did in the previous proof. S x1 is equal to lambda 1 x1. This is the first eigenvalue or eigenvector. And S x2 is equal to lambda 2 x2. I'm going to take the dot product with x2 and the dot product with x1. And utilize, again, it's all in the symmetry of S. Then, lambda 1 minus lambda 2, x1 dot x2 has to be equal to 0. Now I started with lambda 2, lambda 1 not equal to lambda 2, which means lambda 1 minus lambda 2 is not equal to 0. Therefore, x1 dot x2 has to be equal to 0. Which means x1 and x2 are orthogonal to each other. If lambda 1 is equal to lambda 2, the proof is too long. But you have to believe me that there are two vectors that are perpendicular to each other that are associated with lambda 1 and lambda 2. So what have we shown so far is that if S is symmetric, then it possesses 3 real eigenvalues, and it's possible to choose 3 corresponding orthonormal eigenvectors. So I've proved this direction. What if I have a matrix that has 3 real eigenvalues and 3 corresponding orthonormal eigenvectors? Is this matrix symmetric or not? If I have a matrix, I don't tell you anything about it except that it has 3 real eigenvalues and 3 corresponding eigenvectors perpendicular to each other. Is it symmetric or not? Yes, it is. And to prove this, so the opposite direction. Assume a matrix S has 3 real eigenvalues, lambda 1, lambda 2, lambda 3, and 3 orthonormal eigenvectors. P, Q, and R. Since P, Q, and R are orthonormal, use the basis set made out of P, Q, and R. Which means any two vectors in R3, x is equal to x1p plus x2q plus x3r, and y is equal to y1p plus y2q plus y3r. And what do I want to prove now? The symmetry of S. Now how can I prove the symmetry of S? I need to prove that x dot sy is equal to Sx dot y. If you calculate, okay, let's Sx is equal to S multiplied by x1p plus x2q plus x3r is equal to x1. Sp1 is equal to lambda 1 p plus x2 lambda 2q, because Sp, remember Sp equal to lambda 1p, Sq equal to lambda 2q, and Sr equal to lambda 3r. And when you take the dot product y dot Sx, you'll get p dot p is 1, so you get y1 x1 lambda 1 plus y2 x2 lambda 2 plus y3 x3 lambda 3. So this is y dot Sx, and if you take x dot Sy, you will get the same, which means S is symmetric. Now, in the midterm of last year, I asked him something similar to that. That's why I went through it in detail. All right. So, I'm going to visit the statement again, just to explain what everything in it, because there's a very important argument here. We're saying it is possible. Why did I say it is possible? Why did I say it is possible to choose? The reason why I said it is possible to choose, because for some matrices, you have many choices. For example, the matrix Pi. This is a symmetric matrix that looks like this, or is equal to P multiplied by I. If you remember from when we studied eigenvalues and eigenvectors from the previous, in the previous lecture, how many eigenvectors does this matrix have? Do you know one at least? All vectors, exactly. All the vectors in the space are eigenvectors, because all vectors in R3, when I multiply Pix, I'm going to get Px, where P is a number, which means I'm keeping the same direction, I'm just increasing the vector, making it the distance, multiplying it by P. So basically every vector is an eigenvector. So when I say I can choose, so I'm going to choose 3 eigenvectors that are perpendicular to each other. Oh, I have it here. Any non-zero vector is an eigenvector. Spectral decomposition of a symmetric matrix. So, when we, or the result of the previous argument is as follows. If I have a coordinate system here, where S is symmetric, if I choose a different coordinate system aligned with those 3 chosen, vectors of S, you'll find that S in this case is diagonal. And the diagonal values are the eigenvalues of S. And of course, we talked about change of basis last time. There's a translation Q, and Q is made out of P, Q, and R. So how would we show this? It's really, I know that P, Q, and R are perpendicular to each other, and I'm choosing P, that P dot Q equal Q dot R equal P dot R. They're all equal to 0. I'm choosing P, norm P is equal to norm Q is equal to norm R is equal to 1. So they're perpendicular to each other and they form an orthonormal basis. I'm going to take S and multiply it by P1, P2, P3. When I take S and multiply it by P1, P2, P3, what do I get? SB, I get P again. But multiplied by value lambda 1. When I take S and multiply by P1, I'm going to get P1 but with increased length into L1 multiplied by P. So SP is equal to lambda 1P. When I multiply it by Q, I'm going to get Q multiplied by lambda 2. When I multiply it by R, these are the eigenvectors of S, I will get R again, but multiplied by lambda 2. If I consider Q to be made out of P, Q, and R, then this SQ transpose is equal to Q transpose multiplied by, I'm going to make this S prime. S prime is equal to Q SQ transpose, which shows that in this, an S prime is equal to this lambda 1, 0, 0, 0, lambda 2, 0, which shows that in this new coordinate system that's made out of P, Q, and R, S prime is a diagonal matrix with the eigenvalues and eigenvectors, with the eigenvalues of S. And so if you ever have a symmetric matrix, and this is utilized a lot in many numerical applications, if you ever have a symmetric matrix, if you can find the coordinate system, if you can change the coordinate system such that the symmetric matrix is diagonal, it becomes very easy to solve this system of equations that you have. And if you work in the coordinate system of this, if you have a symmetric matrix and you change the coordinate system into the eigenvectors of this matrix, the equations become very simple because you're only you have a lot of zeros and you only have the diagonals non-zero. Now a symmetric matrix is used to describe extension. So if I have an object or this circle here, because the P keeps its direction, Q keeps its direction, a symmetric matrix is used to describe an extension of an object or stretch. So S describes stretch. And since it really, the invariants of a matrix do not really depend on the coordinate system, if I choose this coordinate system, for this coordinate system, it's better to calculate the invariance in this coordinate system. In this case, I1 of S, which is the trace of S, is basically lambda 1 plus lambda 2 plus lambda 3. The determinant of S, which is I3 of S, they're the same whether I use S prime or S. This is equal to the three eigenvalues multiplied by each other. And I2 of S, which will be equal to I2 of S prime, will be equal to lambda 1, lambda 2, plus lambda 1, lambda 3, plus lambda 2, lambda 3. When we're dealing with a stress matrix, we call these lambda 1, lambda 2, lambda 3 the principal stresses. When we use a symmetric matrix, we call these lambda 1, lambda 2, lambda 3. When we use the strain matrix, we call them the principal strains. And the three directions, in the stress we call them the principal stress directions, and in the strain we call them the principal strain directions. So numerically, how would you do any of that stuff? Find the coordinate system in which the following symmetric matrix is diagonal. Just solve it by hand, or just say eigensystem of M. Eigensystem of M, you will get stored in a variable A. When you look at A in matrix form, the output will look like this. Lambda 1, eigenvalue 1. Lambda 2, eigenvalue 2. Lambda 3, eigenvalue 3. So this is the now to form Q. So the new coordinate system is made out of the normalized. You have to make their length 1, eigenvalue 1, eigenvalue 2, and eigenvalue 3. And as long as M is symmetric, these will be perpendicular to each other. So, if you take Q, now this is input. If you define eigenvalue 1 as equal to the second row, the first entry. Eigenvalue 2 is the second row, the second entry. The second row, the second entry. Eigenvalue 3 is the second row, the third entry. Then normalize them. Eigenvalue 1 is equal to eigenvalue 1 divided by norm eigenvalue 1, and so on. Because they're not always normalized. Then if you take Q to be equal to the list, to the matrix made out of the first row is eigenvalue 1, the second row is eigenvalue 2, the third row is eigenvalue 3. When you multiply Q by M by Q transpose, you will get a diagonal matrix that's equal to lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. So we're also interested in a special type of symmetric matrix, or special types of symmetric matrices. They're called the positive definite and semi-positive definite symmetric matrices. Simply because positive definite and semi-positive definite symmetric matrices, especially in numerical procedures, they tell us something about the stability of the problem that I'm trying to solve. In general, what I'm interested in, if this is the force and this is the deformation, I'm always interested in a rising stress strain curve, or rising force versus deformation. Once I have the force decrease while the displacement is increasing, this is an area of instability. This is described by a positive definite matrix, this area, positive definite. This area, not positive definite. So in general, we have that F, where this is a vector of forces, is equal to a symmetric matrix multiplied by a vector of displacements. And we want F dot delta to be greater than 0. Which means delta dot F has to be greater than 0. Which means delta dot S delta has to be greater than 0. For any delta. And this is what we call positive definite. And delta dot S delta greater than or equal to 0, that's what we call semi-positive definite. So a positive definite matrix, S. S is a symmetric matrix that's n by n. S is called so if for every x, for every vector in Rn, x dot Sx is greater than 0, then S is positive definite. And if for every x, and here x is not equal to 0. Because if x is 0, you have to get the 0, x dot Sx would be 0. If for every x belongs to Rn, x dot Sx So if I have a symmetric matrix, and if for every x in Rn, x dot Sx is greater than or equal to 0, then S is semi-positive definite. Now there's a problem or a question here. If S is positive definite is equivalent to saying, so S is symmetric first. So we're given that S is a symmetric matrix. If it's positive definite, that implies that the eigenvalues of S are all positive. Because if you have a negative eigenvalue, for example, if I have here negative 5, 0, 0, whatever number is here, and you say I have a displacement of 1 millimeter in this direction, when I multiply this matrix by this, I will get negative 5. Which means that I have a force, a force of 1 millimeter in this direction, and the force is in the other direction. Which means there is some sort of instability. Sorry? So that's why, for it to be positive definite, for the problem to be stable, all these numbers have to be positive. The diagonals have to be positive. So to prove this, I'm going to prove only one direction. Then for every x dot Sx is greater than 0, choose x to be eigenvector of S, then eigenvector, the S eigenvector is equal to eigenvector dot lambda eigenvector. Lambda is a number, I will take it out. Eigenvector. I know that this is greater than 0, but the dot product of the two vectors is greater than 0, therefore the eigenvalue has to be greater than 0. And the opposite direction is what I asked for in the midterm last year. Alright, so I will give you 4 minutes, because I'm going to now talk about a totally different matrix, Q-symmetric, so I want you to be fresh. 4 minutes exactly from now. I give you a symmetric matrix. If I give you a symmetric matrix, and I tell you that all its eigenvalues are positive, does this mean it's positive then? And there are all sorts of... I had already told them that this was what they were going to see in the midterm. And the proof is short. But all people just went and found books and wrote things that they didn't know what they were talking about. So, one of the students he wrote a huge proof, 2 pages. And so the exam don't come book. He wrote a 2 pages proof. And I mean, it's partly right, but it's not right. So I didn't give him any mark on it. Simply because he said I did it right. I've got a reference. I copied it from the book. I said, okay, that's fine. Sit down. Tell me what this means. What did you write? So you basically just copied what was in the book during the exam, but that's it. Anyway, so what I'm trying to say is that the proof is very simple, and it's similar to the proof. Well, why don't we do this It's the same. This same question will come in the literature. And the proof should be short, and you should understand what you're writing. symmetric matrices. Now, any matrix that you studied before, any matrix can be divided into a symmetric or decomposed into a symmetric part and a skew symmetric part, where the symmetric part is equal to half A plus A transpose, and the skew symmetric part is equal to half A minus A transpose. You already studied this in your linear algebra a few years ago. So, the definition of a skew symmetric matrix is as follows. W is a skew let's take the 3, but we're talking about the 3 by 3 matrix. The transpose is equal to its so the transpose is equal to its negative. So since the transpose is equal to its negative, we get that Wij is equal to negative Wji. And in matrix form, W will have something, will look like this. The diagonal has to be 0. And if this is W12, this has to be negative W12. And if this is W13, this has to be negative W13. And if this is W23, this has to be negative W23. Now let's look at a skew symmetric matrix in R2, just to understand what a skew symmetric matrix does. Let's look at it in R2. Example in R2. Let's take W equal to 0, negative 5, or negative 1. Let's just take the easiest one. And let's see what happens when I multiply W by X, where X is made out of X1 and X2. What will I get? Negative X2, X1. What is that? That's the vector that's actually perpendicular to the original one. So W does the volume. Takes any vector here and gives me a perpendicular vector. I'm just going to put it here. It's time to wake up. So it takes any vector and gives me a vector that's perpendicular. Take any vector here and gives me a vector that's perpendicular. And that's why a skew symmetric matrix usually tells me something that an object is rotating and gives me that direction of rotation. Not necessarily direction of rotation, but if something is rotating fast, it gives me the instantaneous rate of rotation. It tells me, okay, this vector is about to rotate in this direction, or this object is about to rotate in a certain direction. Now, this is in R2. So what does it look in R3? In R3, it looks like this. There is a certain direction around which W doesn't do anything. Or when I multiply this matrix W, capital W, by this direction, nothing happens. I get a 0. And any other vector, when I multiply W by this vector, I get another vector that's perpendicular to this vector, A. It's called WA. And when I multiply the matrix W by the vector B, I get a small vector perpendicular to B that's equal to WB. Now those small vectors that tell me something about the instantaneous rotation of this object have to be perpendicular to both A and this axis of rotation, which is small w. Because this is perpendicular to both, the action of W is equivalent to the cross product between this axis of rotation and this vector, A or B. So this is what it does visually. Now we have to prove that all this is true. First thing we need to address is this vector. And we need to find this vector where when W is multiplied by this vector, I get 0. Because this vector is not rotating. And that's the first problem. If W is a skew-symmetric matrix in a 3-dimensional Euclidean vector space, then we need to show that 0 is an eigenvalue of W. And thus W is not invertible, and 0 is an eigenvalue, and the associated eigenvector is that vector that does not rotate. Since W is a 3x3 matrix, it will have at least one real eigenvalue. Let's call it lambda. Therefore, there is a corresponding eigenvector R. Now I know that WR has to be equal to lambda 1 multiplied by R. I'm going to take the dot product with R on both sides. And I'm going to utilize the skew symmetry of W. Skew symmetry means that I bring it here, will be W transpose. W transpose is equal to negative W. So these are equal to that. Which is also, so negative WR dot R is equal to negative lambda 1 R dot R. Which tells me that lambda 1 R dot R minus lambda 1 R dot R, sorry, plus, has to be equal to 0. Now R dot R is not equal to 0, therefore lambda 1 is equal to 0. Which tells me that there is a vector. When I multiply W by this vector, I get 0. And this is the eigenvector of W corresponding to the eigenvalue lambda 1 equal to 0. Now, there is just some property that I forgot to show you. For every x in R3, Wx dot x is equal to x dot W transpose x. W transpose x is equal to negative x dot Wx. From here, I have Wx dot x plus Wx dot x is equal to 0. From here, Wx dot x has to be equal to 0, which means x, Wx is always perpendicular to or orthogonal to. Whenever I have x and multiply by w, I get a vector that's perpendicular to x. And this is true for the one real eigenvalue as well. For the one real eigenvector as well, which gives me that this the eigenvalue is 0, and it has so there is one real eigenvalue. This is 0, and there is a corresponding eigenvector. So now, if I work in this coordinate system made out of this eigenvalue, so I'm going to call this E1 equal to R, and then I'm going to take any vector here, I'm going to call it E2. I'm going to take any vector here, I'm going to call it E3. What we know so far is that W E1 is equal to 0. So if I multiply W by E1, I get 0. What we will show is that when I multiply W by E2, I'm going to get a number called omega E3. And if I multiply W by E3, I'm going to get a number negative omega E2, where omega is that rate of rotation of that object. So this is what we need to show right now. What we've shown is that WE1 is 0. Now I want to show that WE2 is equal to this number, and WE3 is equal to this number. So if W is a skew-symmetric matrix in a three-dimensional Euclidean vector space, and E1 is the unit eigenvector associated with the eigenvalue lambda equals 0, then show that for every A, WA is equal to this, which is corresponding to saying this omega E1 is the axial vector. I take the cross product of omega A1 with any vector A, I get how this A is rotating. So the action of W on A is equal to this, where omega is equal to E3 dot WE2. So far we know WE1, the matrix multiplied by E1 is equal to 0. What about WE2 and what about WE3? Now WE2 is a vector. Let's call it alpha E1 plus beta E2 plus gamma E3. So the first thing is E2, so WE2 is equal to 0, which means E2 dot WE2, which is alpha E1 plus beta E2 plus gamma E3 is equal to 0. From here, E2 dot E1 is 0, E2 dot E3 is 0, E2 dot E2 is 1, tells me that beta equals 0. So this goes. Also E1 dot WE2 is equal to negative WE1 dot E2 is equal to 0. Which means if I take E1 dot alpha E1 plus beta E2 plus gamma E3 equals 0, from here alpha equals 0, which makes that one go as well. And since I defined this omega as E3 dot WE2 as omega, from here E3 dot, we already took these out. This is omega, sorry, it's clearer in the book. Therefore, WE2 is equal to omega E3. So I've shown you now that when I take that W and multiply it by E2, I get a vector equal to omega E3. And you can show exactly with the same procedure that when I take W multiplied by E3, I'm going to get a negative omega multiplied by E2. Which basically shows that the object is rotating. Similarly, now if A is equal to A1, E1, so pick a random vector. What would happen when I multiply W by A? This is W by all these components. The component in the direction of 1, W does not do any rotation to that. So WE1 is 0. I know that WE1 is 0. WE2 is equal to omega E3. Omega E3 multiplied by E2 minus, when I multiply W by E3, WE3 is equal to negative omega E2 multiplied by A3. What if I now take this omega E1 vector and cross it with A? This is omega E1 vector cross E1 E1 plus A2 E2 plus A3 E3. E1 cross E1 is 0. E1 cross E2 is E3. Which tells me the following. That when I take the cross product between that axial vector and any vector A, it's equal to the action of the skew-symmetric matrix multiplied by A. the matrix WA is equal to the vector omega E1, and E1 is the eigenvalue, eigenvector of W cross any vector A, cross this vector. In a general coordinate system, W has the form 0, W12, W13, negative W12, 0, W23, negative W13, negative W23, 0, and this omega E1 vector has the components negative W23, W13, negative W12, which I'm going to call the axis vector small w. Now, a skew symmetric matrix is used for the following. If I have something that's rotating, then the instantaneous rate of rotation is represented by a skew symmetric matrix. And any skew symmetric matrix, in fact, represents a rate of rotation of an object. And that is only at small rotations. When we study strain in the third chapter, we're going to look at the deformation as a decomposition of two types of deformation. A deformation due to stretch, described by a symmetric matrix, and a deformation due to rotation, described by a skew symmetric matrix. But a skew symmetric matrix only applies when I have small rotations, as I will show you right now. If Q is equal to cosine 30, T, sine 30T, negative sine 30T, cosine 30T, Q dot will equal to let's say that an object is rotating just want to find a nice example. Cosine 30t, sine 30t, negative sine 30t, cosine 30t. When you take Q dot, you're going to find here x, or a number a. Let's call this a. And you're going to find a number here, negative a. And here you're going to find b and b. At the beginning of the rotation, t equals 0. Cosine 30t is actually equal, the Q dot t equals 0, and cosine 30t dot will be related to sine 30t multiplied by 30, which means that this will be 0. Sine 0 is 0. Which means that Q dot is a skew symmetric matrix at small rotations. This is just an example, and I'll prove it right now. So we know that Q transpose, when an object is rotating, and if Q is a function of t, is always equal to I, whatever the time is, because something is rotating. Q is always a function of time. Q multiplied by Q transpose. Because Q is a rotation, Q multiplied by Q transpose is always equal to I. Now d Q transpose by dt is equal to the zero matrix, because I is constant. When I take the derivative of the matrix with respect to time, I'm taking the derivative of each component. The derivative of Q transpose by dt is equal to 0. Therefore, Q dot Q transpose plus Q transpose dot is equal to 0. Q dot Q transpose is equal to negative Q dot transpose. At the beginning of the rotation, Q is equal to Q transpose is almost equal to I. Before I actually start, just right when the object is about to rotate, the original Q, the rotation matrix, is equal to I, which means I haven't rotated yet. And you'll see that Q dot will be equal to negative Q dot transpose, which means the Q dot is a rotation, is a skew symmetric matrix. So the instantaneous rate of rotation Q dot is represented by the skew symmetric matrix. So Q dot is a skew symmetric matrix only at the beginning of any rotation. Also, any skew symmetric matrix represents a rate of rotation. What we're trying to say is that if I add I plus this rate of rotation, W, multiplied by dt, let's call this matrix A. What I'm trying to say is that if I add I to W, then A is a rotation. Because this describes its rate multiplied by dt, I should get a rotation. So let's see. A transpose is equal to I plus W dt multiply I plus W transpose dt, which is equal to I plus W dt. W transpose is equal to negative W, so negative W dt plus W transpose dt squared. This cancels this, and at very small time, this is equal to I. Therefore, A is a rotation matrix, and W, the skew symmetric matrix, is its rate. In the next problem, we want to show what happens if you take the components of a symmetric matrix. If you multiply a symmetric matrix by a skew symmetric matrix, and then you take the trace. So SW is a matrix whose components are S, I, W, J, and K, K. The trace of SW is equal to the sum I equal 1 to 3 SW II, which using the summation convention is equal to SW II, which will be equal to SIK WKI. Because of the symmetry of S and the skew symmetry of W, it's very easy to show that this is equal to 0. There is another problem in your text for visualization. Of this Q symmetric matrix on an object. So, the next topic is higher order tensors. First order tensors, second order tensors, third order tensor, fourth order tensor. So, if I use an orthonormal basis set E1, E2, and E3, prime is another orthonormal basis set E-1, E-2, E-3. And if the translation between this one and this one is using Q, a vector here U is made out of components U1, U2, U3. The vector in the new coordinate system is equal to QU. And U, a component of U, is given, U has only one component, UI, and U prime has only one, basically has one index, I, and U prime has one index, I. This is called first order tensor. If I have a matrix here, the matrix is equal to M11, M12, M13, and so on. The new matrix in the new coordinate system is equal to QM, Q transpose. The components of M here are called Mij, where I takes from 1 to 3, J takes from 1 to 3, so I have 3 by 3 components. M prime Ij is equal to QM, Q transpose. I goes to the first, J goes to the last, but because it's transpose, it's going to be here. And then in the middle, K, K, L, L. This is called the second order tensor. The definition of second order tensor, or first order tensor sometimes is given as a component or a quantity whose components change according to this relationship when you choose a new coordinate system. A second order tensor is a quantity, a 3 by 3 matrix of numbers that when you change the coordinate system, it changes according to this relationship. Third order tensors and fourth order tensors are similar quantities but with more indices. So let's see what is a third order tensor and what is a fourth order tensor. A third order tensor is a linear map. Let's call it D. It takes a matrix and gives me a vector. So how would such a map work? How would such a map work? For every matrix, M11, M12, M13, and so on, D will have 9 constants. So in component form. D, J, K will be the constant that's multiplied by J, K, because M11 will need a constant. M12 will need another constant. It's a linear map. I'm multiplying all these numbers by constants, and so each component will have a component or a constant that's multiplied by it. But the resulting thing, because it's a linear map that takes from M3 to R3, the result has to be a vector. Because the result has to be a vector, for all those 9 components are repeated for every component of the resulting vector, which means I have 3 by 3 by 3 components. So if I have a third order tensor for every matrix gives me a vector, it will need 3 by 3 by 3 components. Because every matrix has 9 components. If I multiply constant by each of those components and I add everything up, I get 1 component in the resulting vector. Then I repeat for the second vector, component, then I repeat for the third component, I will get 3 by 3 by 3 components for D. If I change the coordinate system, the resulting, the new D, I, J, K will be equal to Q, I, Q, J, Q, K, the old LMN. We're summing over L, we're summing over M, we're summing over N. And this is called the third order tensor. If you notice, M prime ij is equal to Qi, Qj, so I goes to this Q, J goes to this Q, and then KL MKL. This is the same thing here. The third order tensor in the new components of the third order tensor IJK is equal to QIL, QJM, QKM, and LMN are sums multiplied by DLMN. The fourth order tensor is a linear map that takes a matrix and gives me another matrix. So how many components does C have? 81. So C has 81 components. C, I, J, K, L, 3 by 3 by 3 by 3. When the coordinate system is changed from B to B prime, the new components are equal to Q, 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 C, here I, J, K, L, M, N, O, P, M, N, O, P. Now, does anybody know any examples of a fourth order tensor? What's an example of a fourth order tensor? It's not the stiffness, it's close to the stiffness. What's a fourth order tensor? What are we going to study in this course? We're going to study the stress, which is a matrix, and the strain, which is a matrix. The relationship between the stress and the strain is a relationship between two matrices. For every stress matrix, I have a strain matrix. For every strain matrix, I have a stress matrix. This relationship is described by a linear map that is called the fourth order tensor C. Now, just one note before I give you another break. When I change, which we will study in chapter 4, no, chapter 5, constitutive laws. When you look at this relationship, that tells me that this fourth order tensor changes its components when I change the coordinate system. Now, if I have a linear elastic materials, what do I expect? If I have a linear elastic isotropic material, what do I expect? What do I expect the relationship between the stress and the strain to be? I expect that this relationship is not dependent on the coordinate system. So I expect that whatever coordinate system I choose, the new C will be exactly the same C. And this is something that you're going to have to do in chapter 5. To find what are the possible C's such that even after you change the coordinate system, C prime I, J, K, L has to be equal to C, I, J, K, L. Linear, elastic, isotropic materials. Because it's an isotropic material, the relationship between the stress and the strain does not depend on the coordinate system. Because the relationship between the stress and the strain does not depend on the coordinate system, these two have to be the same. Alright, we'll give you 45 minutes.